Good evening, ladies and gentlemen. How is everyone tonight? Great. Good, excellent. Well, thanks for coming out to join us for this March edition of the Von Karman Lecture Series. 10 years ago this month, the Mars Reconnaissance Orbiter arrived at Mars. It has sent back thousands of high-resolution images and more data than all Mars missions combined. And a few other things. It has found the strongest evidence yet that liquid water flows intermittently on present-day Mars, found evidence of diverse watery environments on early Mars, seen seasonal changes and longer-term changes over the last decade, and caught avalanches and dust storms in action. Originally slated for a 2-year prime mission, followed by a 2-year relay mission, MRO has certainly paid its dues. It has probed the planet's atmosphere, surface, and subsurface with unprecedented spatial resolution and coverage, and its 7 science investigations and 6 instruments have returned more than 250 terabits of data, enabling numerous discoveries. At the same time, MRO has rendered invaluable service to landers and rovers at Mars. It not only delivered critical information for the selection of landing sites, but also captured crucial data and historic images during the arrivals of the Phoenix lander and Curiosity rover. It also frequently serves as a relay for data and commands between those spacecraft and Earth. As NASA's Mars exploration program looks to the future, MRO continues to characterize and certify new landing sites for both NASA and the European Space Agency, while preparing to cover critical events and surface operations for the InSight lander, Mars 2020 rover, and other future missions. Tonight's guest graduated in 1990 from the University of Arizona, majoring in applied math. During her studies, she had an internship at JPL. After graduation, she was hired back to JPL to work as a science coordinator for an experiment aboard the Galileo spacecraft. A few years into this job, she returned to continue her education at UCLA, go Bruins, where in 2000 she received her PhD in geophysics and space physics. There she studied water ice clouds in the Mars atmosphere. Using Viking orbiter data, she was able to detect and map the clouds over the course of a Mars year, which showed for the first time that Mars has a nearly constant, widespread cloud cover. She has also been the science lead for many future mission proposals and studies, including those for Mars, Europa, and Titan. And she served as the deputy project scientist for the Mars Science Laboratory during its initial days. In 2002, she was invited to be a co-investigator for the atmospheric studies on the Phoenix mission, and in 2003, she was invited to become the Phoenix project scientist. She was also the deputy project scientist for the ExoMars Trace Gas Orbiter in a prior era when the U.S. had 4 contributed instruments. Currently, she is the deputy project scientist for the Mars Reconnaissance Orbiter. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Leslie Tampari.
Thank you. Thank you very much for coming. I'm really excited to be here. I really want to tell you all about the things that we've done in the last 10 years with the Mars Reconnaissance Orbiter. It was really incredibly difficult to try to take 10 years of amazing discoveries and stick it into a talk, so I've tried to cherry pick a few of my favorite things and give you a broad brush overview of what we've learned in the last 10 years. And I just want to point out here on the cover image, this is actually the Earth and the Moon, and that's taken from MRO at Mars with our high-resolution camera. So it's pretty neat. It's a very good camera. Okay, so our outline here. We're going to talk a little bit about why should we explore Mars. I'm going to give a little Mars Reconnaissance Orbiter overview. We'll talk about the science results, of course, and then I'll tell you a little bit about our support for other missions that we're doing. Okay, why should we explore Mars? Well, Mars is thought to be similar to Earth in many ways. And in fact, in Mars's ancient history, there's evidence that there was liquid flowing water on the surface of Mars and catastrophic floods. So the questions are, how could that water have been present in ancient Mars times, and where did it go? And one of the hypotheses is, of course, it had a thick atmosphere at that time, which it doesn't today. And liquid water today is not stable on the surface of Mars. But since it has evidence for past liquid water in a more clement environment, we want to know, why was there life ever on Mars? Did it arise on Mars? Is it still there today? Could we possibly find fossilized life, fossilized microbes on Mars sometime in the future? Also, if it had this early environment that was much more Earth-like, what happened? Where did that atmosphere go? Where did the water go? How did it change? We want to understand those details, and that helps us learn more about the Earth as well. And then finally, we've explored all the ends of the Earth. We've gone to the Moon. the next step is going to Mars. So we want to prepare for human exploration to go to Mars. So with these sort of big picture questions in mind, the Mars exploration program has 4 main goals. And those are, of course, to determine if life ever arose on Mars. We want to figure out what kinds of environments it would need. We are also studying the climate and these climate changes. What are the current climate processes? What are the ancient climate processes? How did the climate change over time? And the geology, the surface tells us a lot about what happened in the past because it leaves a record of carved channels and various things. And it also tells us about the environment in terms of whether or not it was habitable or not, because it can record, we can see minerals on the surface which record different environments. And then, of course, we're preparing for humans. And the cross-cutting themes here are, of course, water and the habitable zones, and then also searching for signs of life. But MRO does not do the third one. It only can address the water and the habitable zones. So I'll talk a little bit more about that. Okay, so a little brief overview of the Mars Reconnaissance Orbiter. Here it is, and for those of you in the room, we have a nice half-scale model right in the back of the auditorium. So after the lecture, if you have a moment to go back there and take a look at it, please do so. But for those of you who are online, you'll have to look here on the screen, and we can see this artist's concept. We can see the big antenna that we use to relay all of our data. As you heard earlier, we send more data than all of the other Mars missions combined. And we have these big solar panels. And then in the middle is our spacecraft with the spacecraft instrument deck pointed down towards the surface of Mars. Okay, here's a couple of nice images of it while it was being assembled at Lockheed Martin in Denver. On the left, you see the spacecraft itself. And then on the right, you can see it way in the background as it's getting ready to go into a test chamber. So it was built, it was sent to Cape Canaveral, and it launched on August 12th, 2005 on an Atlas V rocket and on its way to Mars. It spent 7 months getting to Mars, and on March 10th, just over 10 years ago, in 2006, it arrived at Mars. And we used 6 engines that burned simultaneously for 27 minutes to slow us down and capture us into the Mars orbit. Then we were in an elliptical orbit at that time, and so we needed to aerobrake. And so what we do to aerobrake is we use these huge solar panels, and we dip down into the atmosphere about 100 kilometers or 60 miles above the surface and use the atmospheric drag to slow down the spacecraft. And we do that for about 6 months to get into a circular orbit that we call the mapping orbit. And that now is where we are today, mapping orbit. It's about 300 kilometers above the surface, or 200 miles. Okay, so here are the experiments that we use. You can see on the top are all of the ones that we use to examine the surface. We have CRISM, which is a mineralogy mapper. It's the one that detects the different kinds of minerals and tells us what they mean. And that's about 18 meters per pixel, or about 50 feet per pixel. HiRISE is the big camera. It's the size of an oil drum. Its resolution is about 30 centimeters per pixel, or foot by foot, so we could resolve this stage, for example. We also have the context camera. The high-resolution camera was such an improvement over the past imagery that we had that we needed to fly sort of a medium resolution, still good resolution camera in order to place these strips of super high resolution data into context so that we could really tell what we were looking at. Then, as you heard earlier, we also, not only do we look at the surface, but we look at the subsurface. So we do that with our SHARAD subsurface radar. And that tells us the depth profile of the surface. We can see from about 10 meters deep and down maybe through the ice cap down to about 2 kilometers maximum depth. We also look in the atmosphere. We look above the surface, and we do that with our MARCI and our MCS experiments. MARCI is a weather camera. It sees limb to limb as MRO is flying over Mars every orbit, and so within one day, because MRO orbits Mars 12 times a day, it builds up an entire global map of Mars every day. The MCS experiment is our atmospheric profiler, and that looks forward of the spacecraft as we're flying, and it sees the different layers in the atmosphere. So it can tell the temperature profile, it can see layers of dust and layers of water ice. Okay, so with these experiments, we're pursuing the Mars program themes of follow the water and search for habitable zones. And in terms of following the water, we're searching for those ancient aqueous minerals to tell us if there was water in Mars's history. And we use our CRISM mineralogy mapper for that. We also are looking for corresponding water-related landforms, because those together will tell us a better picture, and you'll see some of those data. We use, of course, our cameras for that. We're also looking at the subsurface water ice in the polar caps and in the mid-latitudes with the SHARAD radar. and the atmospheric water ice with our weather instruments. We're also, in the terms of searching for habitable zones, CRISM, our mineralogy experiment, can detect those minerals, different kinds of minerals. It can tell us if that environment where those minerals formed was a neutral environment or very acidic, how much salt was there, and you'll see some examples of those coming up. Also, of course, the landforms, again, are important here because we want to know if these environments were habitable for life, and the whole context of everything that we put together will tell us that story. And of course, understanding the present-day climate is really important to try to understand what the past climate might have been. Okay, science results. Okay, we can separate the science results into sort of three main timeframes on Mars. We have ancient Mars, which is really ancient, about 3.7 billion years ago and further back. And then I'll talk about recent Mars, which by that I mean the last several hundred thousand years. And then present Mars, and that's today. What's been going on today, what goes on every day, what's been happening in the last 10 years. Okay, so in terms of ancient Mars, we've learned that there are many, many wet environments, and some of them appear to be habitable. So looking back 10 years ago, before MRO got into orbit, what did we know about ancient Mars? Well, we knew it was wet. We had this nice Viking image that showed what we call dendritic channels, and those are channels that are similar to what you might see if you're flying in an airplane over a mountain, where you see rivers that come down and they sort of coalesce and form bigger and bigger channels. So we think that's evidence of sustained rainfall on Mars. So we knew it was wet, but we didn't know the extent of the different types of environments, and we didn't understand if they were habitable or not, if they had a neutral environment or an acidic environment, and we certainly didn't understand how many there were. So I'm going to tell you what we're looking for in terms of some of these minerals from an Earth analog perspective. So we're searching for these minerals and corresponding landforms that tell us about the ancient environments. So here's an image from Earth of a deltaic sediments. So a river delta comes and flows into maybe a standing lake or something like the Gulf of Mexico, and it deposits clays. And so the clays are something that we would look for, plus the landform morphology, to see if we see river deltas. We're also looking for minerals such as sulfate and chloride and carbonate in combinations, because those might have been left over after a lake bed evaporated. We also are looking for evidence for hot springs. We know that hot springs would produce hydrated silica, which is like opal, clays, and iron oxides. And then finally, we know that some of these minerals can metamorphose over time with different environments of pressure and temperature to create even different minerals. So we have phyllosilicates, such as chloride and serpentine, and other kinds of silicates, such as prehnite. Okay, so what did we learn? We learned there are river deltas on Mars. This is totally cool. So you can see here a channel coming down and flowing into a crater, and you can see the morphology of what looks like a delta. And we see that there are clays at the margins and that there are carbonates that probably precipitated out. And because there are carbonates there, carbonates are a neutral pH. So that tells us that there's a lot of water, it was a neutral environment, this was likely a habitable location. We don't know if it was inhabited, but we know that it might have been habitable. Okay, another kind of example that we see is in a place called Marthalis, and we see this transitional environment. And so going up section from the red to the green, or the red over here to the green, we see the older or more well-preserved layers, and we can see that those are iron and magnesium clays. And those were formed in a neutral environment. There are different oxidation states, which may have been provided energy for microbes. And then we see that above that, there's some acid-altered clays. And above that, there's aluminum clay and silica, which is in fact what you get if you acid leach the iron and magnesium clays. And then above that is even more amorphous material. So all of these minerals required a lot of water, and it shows that the environment transitioned over time. And so this is possibly a habitable location, at least in the older or more well-preserved sections where it was a more neutral environment. And one of the things that we are discovering is that Mars seemed at one point to have transitioned from a wet and neutral environment sort of linearly to a more acidic and dry environment. And we see some of these transitions on Mars, and we're learning that maybe it's more complicated than that. And what we found when we started before this mission started, we knew that there were some hints of this, but we had no idea the amount that were here. And so you see on this map, there's a whole bunch of different kinds of minerals, and they're all over the place, and we have thousands of detections of these now. And we're trying to make sense of it. And we think that there's some evidence now that maybe it's not as simple as a linear transition in time, but maybe even at the same time, but at different locations, there was different kinds of environments. Or maybe Mars transitioned as a whole back and forth multiple times over Mars's history. Okay, so moving on to recent Mars. We're interested in ice and polar caps and climate change. So back in 2005, we knew that there were polar caps on Mars, of course. Mars has an axial tilt very similar to the Earth's, 25 degrees. And because of that, of course, it has seasons like the Earth has seasons. So in the northern hemisphere, when it's wintertime, the atmosphere condenses out as a polar cap. And the atmosphere is 95% carbon dioxide, so it condenses out about 15% of it as a dry ice polar cap. And then in the summer, when the seasons change, all of that comes off and goes back into the atmosphere, goes to the South Pole to make polar cap there. And we're left with what you see here is a residual water ice cap. And this residual water ice cap, we knew had layers because we could see them, shown in a false color image here to emphasize the layering. We could see them at the margins, in the troughs and at the edges of the polar cap. But we really had no idea how deep the polar cap was. Did these layers go all the way through? This tilt that Mars has that causes the polar caps and causes the change also varies over 100,000 year time scales. So it goes from 25, where it is today, to 45 and back up to 0 over long time scales. And that would cause the polar cap to maybe completely sublimate and go into the atmosphere, and you should get ice forming elsewhere, for example, in the mid-latitudes. But none of this was really confirmed, and we had a little information about it at the time. So we have our subsurface probe, the Sherrod radar. And so as MRO flies over the polar cap, it can probe the surface under where the spacecraft track is. And so you can get these vertical sections, as shown here, of what's going on in the polar cap. And you can see at the top that you can see some of these troughs and chasma, and then you can see tons and tons of layering in here. And those are all different layers of ice and dust, or different amounts of dust mixed with the ice. And then what we found for the first time, we could see all the way to the bottom here in this blue line, so that we could see the total depth of the Martian North Polar Cap. It's about 2 kilometers deep, and so it contains as much ice as about 1/3 of the Greenland ice sheet. Okay, we've now been at Mars for 10 years. We've had many of these transects. We can put them all together in a sort of a database, and we can produce a 3D image, basically, and we can take any cut that we want through there and sort of interpolate between the points that we have because the coverage is so good. And we can find all kinds of interesting things. So you see here, you'll recognize the main polar cap here with the big Chasma Boreal here in the center. But what we can now see with this is that there are buried chasma. There are also these circular features that appear to be craters that happened in some ancient time in Mars's history when the polar cap was exposed at that level and then later covered up. Okay, transitioning to the South Polar region. There's also a South Polar Cap. It in the summertime, there's a residual polar cap that actually has a veneer of carbon dioxide or dry ice on top of a water ice layer. And we thought that it was completely water ice underneath that for a while, but what we've learned is that's not the case. And what you're seeing here, there's a color scale on the right, that's 1,000 meters in the red. You're seeing that we found buried carbon dioxide within the polar cap. And there's 1,000 meters, more than half of a mile of buried CO2. This is enough CO2 that if it were all sublimated, it would double the current atmospheric pressure on Mars. So that's a pretty big amount. It's not necessarily enough to bring Mars to a tropical paradise, but it's enough to make some places and some seasons be able to sustain liquid water. So this was a pretty major advancement. And you can see here in the Sherrod radargram that you see the surface, then you see this what's called a radar reflection-free zone, and that's because CO2 does not do a good job at reflecting that radar, whereas the ice layers do a very good job. And you can see the embedded ice layers in the center. And now we think that, in fact, This is over the last 600,000 years that it's transitioned multiple times, and you get some CO2 condensing, you get a water ice veneer, that doesn't completely come off, and then you get some more CO2, and you get these layers building up. So it's teaching us about the climate history of Mars. And finally, because there are these climate changes, then there should be some ice at mid-latitudes. And we had seen these features called lobate debris aprons. We like to name things as a descriptive name, without saying what caused it, because in the beginning we don't necessarily know what caused it. So lobate means lobe-like, and you can see here that there are these two, well, there's a couple features. There's one up here too, but there's one here and one here in particular. LDA is lobate debris apron. And you can see in the blow-up that it has this margin, which is sort of lobe-like, and it appears that these are sort of mountains with these flow features flowing off of them. Well, what would flow? Ice would flow. So we thought, well, maybe they're made of ice. But we couldn't confirm that until we had Sherrod. So also in the right-hand image here, you can see arcuate ridges, which is exactly what a flowing glacier down a mountain slope would look like. So with Sherrod, we were able to take these transect crosses across these lobate debris aprons, and we were able to confirm, at least for some of them, that there is in fact ice beneath them. And in fact, it's about 95% ice. So we've kind of confirmed that there is recent climate change on Mars. It's more complicated than we thought. We're still learning about it, and there's much more to learn. But we found some of these key signatures that are supporting this climate change that we think is happening. Okay, going on to present Mars. So present Mars can be characterized as unexpected changes. So what did we know about present Mars back in 2005? Well, we knew that there probably was no liquid water stable on the surface of Mars because the temperatures and pressures are so low. We did know that there were dunes, but we thought that maybe they were frozen in time because, again, with the very thin atmospheric pressure that we have today, it's really hard to lift sand grains and keep them moving. So it's hard to move dunes in mass. In fact, who here has read or seen The Martian? Yeah, many of us, right? So in the very beginning, there's a huge dust storm that comes, and it's going to threaten to knock over the rocket, and it blows equipment around, and it blows the astronaut around. And anyway, that couldn't really happen because, in fact, the atmospheric pressure is only 1% of what it is on the Earth. So even if you have a really fast wind, like a 100-mile-an-hour wind, it would really feel like a 10-mile-an-hour wind on Earth. So, but I'm an atmospheric scientist, so I give him artistic license on that one. We also had never seen the vertical distribution of dust and ice. We'd seen sort of column, from the top down, we'd seen column abundances, but not where the layers of those dust and ice clouds are. And we hadn't seen impact cratering. Obviously, we had seen lots of impact craters on the surface, but nothing ever happening today. And we've subsequently seen many of these things. And the polar cap formation, again, we're interested in trying to understand how does that polar cap actually form. We know that CO2 condenses out, but does it form as a frost, just forming frost on the surface as it builds up, or does it actually snow? So you'll see some results on that. And these are actually MRO images. I didn't really have a good place to put in dust storm images, and I just wanted to highlight these. This is a beautiful local dust storm, and this is actually the North Polar Cap in early spring, so that the CO2 frost is way south, and you can see this nice low pressure system kicking up a lot of dust. And those are from our Marcy camera. Okay, so Mars is incredibly dynamic. This is one of the things that we have learned. It's got stuff going on all the time, all over the place. You can see here that we have active gullies. We have avalanches. Those are in the polar region. We have dunes. We have gullies on dunes. We have dust devils. We have new impact craters, lots and lots of those. Those are all of the red dots that are all over the place here. Lots and lots of active impact craters that we've seen. Polar pits, RSL, which I'll talk about in a minute, and some of you may have heard about from last fall. Robots, yes, we have Curiosity and Opportunity that we watch moving around on the surface, and other North Polar and South Polar features. So one of the things we've learned is Mars is a very, very dynamic place. So here's the RSL. So RSL stands for Recurring Slope Lineae. And again, it's a name that doesn't imply what causes it, it's just describing it. And what you see here in the movie is that these are all on steep slopes, and when those slopes get warmed seasonally by the sun, these features tend to darken and lengthen. And then as the season cools, the features fade and disappear. And the next year, they recur. So recurring slope lineae. And we've studied these for a while now, and we think that they're most sort of analogous with a liquid water flow. But it's hard to imagine how that could be the case, right? The atmosphere is too thin. The temperatures are too cold. How can you have liquid water on Mars? Well, maybe in some extreme cases you can. And in fact, we turned our mineralogy experiment, which can see salt, to look at these. Now remember, HiRISE has a 30 centimeter by 30 centimeter pixel size. Our mineralogy experiment has 18 meter by 18 meter pixel size. So we needed an area that was very dense with these RSL. And so you can see the image here. We put some pixels on there. And we were looking for evidence of the minerals that might be here, and in fact, hydrated minerals. So on the right, you can see spectra of laboratory minerals. And you can see that it's very clear that at various wavelengths, which are sort of like different colors of light, there are these absorption features. And lo and behold, when we targeted CRISM here, we saw absorption features at the very same places. So that tells us that these are, in fact, hydrated perchlorates. So that's really a salty water, or perhaps you might think of it as a watery salt. These particular kinds of salts are very deliquescent, which means that they very much like to suck up water from wherever they can get it, the atmosphere or wherever else. If I put a cup of perchlorate salt here on the table, I think by the end of my talk it would have self-liquefied just by pulling water out of the environment. They also, like you would salt the roads in Denver, for example, where there was a big snowstorm that my colleague just got trapped in, you salt the roads to lower the freezing temperature. This salt will also lower the freezing temperature, but instead of to minus 4 degrees or so, which is what the sodium chloride salt does that we use on the roads here, it depresses it to minus 70 degrees Celsius. So that means that even today, there are places and locations where with this salt, you might be able to have liquid water. So these RSL, they look like a duck. They're starting to quack like a duck. We're not really quite ready to call them a duck yet, because it's still like, where does it get all the water? It should require a large amount of water to actually liquefy and make these features flow. They're not gigantic, but they're not small by any means. And the atmosphere doesn't have a whole lot of water in it. If you take the entire amount of water in the atmosphere and you collapse it down, it's less than the width of one of my hairs. So it's very little water. Okay, moving on to windy Mars. Okay, remember, we didn't think these dunes were necessarily moving. Well, we found they do move. So we've also learned that it is possible in gusts of winds to pick up sand, and then once that sand gets lofted, it's easier to stay lofted, and that's what's helping these dunes move. And you can see that not only have we seen this one example, but this map shows that all of these dark spots are active dune fields that we're currently monitoring. The white ones are dune fields that we know of that we haven't yet seen move. But with every passing year, it's a longer baseline to be able to look at a before and after image. And so maybe they're just moving slower. We have to keep watching to find out. Okay, impact craters. So we know that Mars is heavily impacted, but we didn't know if we would ever see a current impact. And in fact, we've seen many, as you saw in the earlier graph. This one in particular is one of my favorites because with our Marcy weather camera that sees globally, limb to limb every day, we can pin down this timing to one day between March 27th and March 28th, 2012. And so you can see this big dark spot, and that was a potential impact crater. Usually what happens is when we discover this in either a Marcy weather camera image or our context imager, an alert goes out to the team, and the HiRISE camera team, and later on, if possible, the CRISM mineralogy team will target these to follow up on them. And so here are some of the impact images from HiRISE on some of these recent impacts. And what you can see here is that the impact has excavated a whole lot of white stuff. Well, that white stuff is ice, and it's nearly pure ice, and it's at lower latitudes than we expected. So this is telling us that even in recent times, there was more water in the atmosphere than we had thought. Okay, so moving on to looking at the atmosphere. This is kind of like our Marcy weather camera. Our MCS profiler also takes data every day, 12 orbits a day, and so you kind of can build up a global picture, a global snapshot of the atmosphere. And what you're seeing is temperatures here, warm temperatures in the bottom and cooler temperatures aloft. That was the North Polar region in spring. here in the equatorial region, you're seeing many, many layers of different temperature regimes. So that's very interesting. We'd never really been able to see that before. Again, this is over the Gale site. You can see lots of temperature variation. And now moving to the south polar region, it's polar winter, and you can see that the surface temperatures are very much colder because it's nighttime there for many months. But aloft, there's air masses that are coming in and descending over the pole, and so they're heating that air as they compress as they descend. Just like when you put air in your tires, it heats up as it compresses. So we get global daily snapshots of the temperatures, the water ice clouds, and the dust clouds. Okay, the Marcy weather camera. You've been waiting for this because I've mentioned it so many times. This is a daily global weather map. This is a recent one from March 7th, and you can see on here many of these features. We can see ice clouds on the left-hand side above the big volcanoes on Mars. You can see the south polar CO2. You can see the north polar residual cap up here, and over here you see that it's a little bit obscured with some orangey stuff. That's dust in the atmosphere. There's local dust storms going on over there. And the big impact crater basin, Hellas Basin, has not only water ice clouds, but also surface frost because it's winter down in the southern region. Okay, and here is our snow, our evidence of south polar snow. The red dots are CO2 snow in the atmosphere, and the white dots are CO2 snow that's just landed on the surface. And you can see the black line is showing us the edge of the extent of the CO2 polar cap at that season. And this is marching along in season. And you can see that first you see the red dots, and then you see some white on the surface. Okay, this is summer, so there's no snow going on, but it'll expand back out. But this is really interesting and exciting to be able to see snowing in the Mars polar region in the current day. And so we can understand the processes that are helping to form these polar caps every day. We used to think that it was just ground up. It was just frost formation right on the ground. And now we know that there's a lot of snow going on. Okay, so I also want to tell you, not only are we a great science mission, but we support a lot of other missions as well. Of course, one of the key ways we support the other missions is by our science itself. A lot of our data taking and the interpretation that is done and presentations and sharing that information leads to interesting places for rovers to go. So in fact, here on the left, you see Gale Crater and the MSL landing site area, and that was, one of the reasons that this area was picked was because of the MRO data and science that came out of that. On the right-hand side is Nili Fosse. It's a crater that has a channel coming into it. You can see in the insert down here that there's a layer of something different. That's carbonate. So that's possibly a habitable location with a former standing lake. And so that's a site that's currently being evaluated and discussed and researched and is a possible landing site for the Mars 2020 rover mission. Okay, and we also, not only do we contribute science analysis and interpretation, but we also help other missions in terms of landing site safety. And this story is very near and dear to my heart because I was also on the Phoenix mission. So back in 2006, before MRO got into its mapping orbit, we were happily planning to land in some North Polar region in one of these boxes. The A and D boxes looked like the ice was too shallow for us. We were going to dig down and search for ice. The C box, the ice was too deep, but the B box was just right. So we were super happy. We were planning to go there. We had some imagery of the location. We could see that it looked like old, very degraded craters. We thought, okay, they're old, they're degraded, they've been bombarded by impacts over Mars's history. It's probably all pretty benign environment. Well, just before, or just after aerobraking and just before the official start of the MRO science phase, MRO took a picture in this landing site for us. And it literally was on Halloween in 2006. And Alfred McEwen, who was the PI of the HiRISE team, sent to Peter Smith, the PI of the Phoenix team, a greeting card, a Halloween greeting card. And this is what it looked like. And what you're seeing here is a 15-meter scale bar. It's littered with boulders everywhere. These are bus-sized boulders. Okay, a half-meter rock would have killed our spacecraft. And this is a 50% rock coverage in bus-sized boulders. This was definitely not a safe place to land. And thank goodness for MRO, because otherwise we would have landed there and failed. So then we said, oh my gosh, MRO, will you please image in this whole annulus and tell us if there's any safe place to land? So they started peppering images around, And we got another greeting card on New Year's Day, 2007, and it showed this. This is a different scale bar, but it's a smooth, flat, polygonal terrain, which is indicative of near surface ice, 5% rock coverage, much safer place to land. So we went there. Okay, we also support entry, descent, and landing. This is a beautiful image that HiRise took of the Phoenix when as it was coming in on its parachute. You can see down in the corner in the inset. Also, after it's landed, we can see images of the parachute and the lander on the surface and the heat shield, and then the Phoenix itself with its solar panels deployed. Similarly, with the Curiosity rover, we captured a beautiful image of it coming down on its parachute, and then the parachute later on the right, we imaged that over a series of time, and you can see that the winds are actually moving the parachute around. And then we support weather reports for solar-powered rovers, for example, Opportunity. If there's a dust storm coming, they want to know because they might need to go into power-saving mode since they're solar-powered. So Opportunity here is at the edge of the crater, and you can see a high-rise image here of Opportunity, and you can actually see the shadow of the camera mast. Pretty incredible. So we've also imaged Curiosity on the surface. You can see its landing area. You can see the nice rover tracks as it went over to its first extended stay at Yellowknife Bay. And we also return their data. We're a data relay asset for them. They can't communicate with very much bandwidth directly to the Earth, so they relay it to us, and we relay it to the Earth. And so we're currently returning 75% of the Curiosity data, which is about 450 megabits per day, and a total of 515 gigabits over the course of their mission. So I'll just want to leave you with this beautiful slide that, of course, 10 years in orbit, we've returned 263 terabits of data. We've traveled almost 1 billion miles since launch from the Earth, 45,000 orbits around Mars. We've been helping out 7 other missions and many, many images. And with that, I'd like to just say thanks to everybody for coming, and I'd like to take questions. And please use the mic if you would like to. We're recording it and everything, so we need to use the mics if you want to ask a question. So go ahead, hop up.
When H.G. Wells described the War of the Worlds, he talked about great intelligences on Mars coolly and dispassionately observing events on Earth. Looks like you folks have turned the tables. Thank you.
Right, thank you.
You mentioned the ice that gets exposed when there's a crater at the lower latitudes. Mm-hmm. Do you have any data on whether that's enough ice to be useful for visiting Mars and getting water?
Yeah, that is one of the things that astronauts or people planning for humans to Mars are certainly interested in. We think it's maybe a couple meters of ice, so it should be enough. I mean, it depends on how much they need and how much area you can excavate. The other thing that's being looked into is actually extracting the water part out of hydrated minerals, which sounds like it might be a much harder task, but it's something that you can do in a place where there's no accessible ice. And so, but even that, they would want to be able to process a huge amount of sort of dirt and soil to be able to extract that water. But that's being worked on too.
Thank you.
What is the definition of life for missions like this, and how would you prove it if you found it?
That is a very difficult question. I am not sure if anybody actually knows the answer to that. MRO is definitely not a life detection mission, so we might see it and not know what it is, but I think you have to look at the certain elements that are involved, and I'm not an expert in that field, so that's about all I can say for you.
One of the biggest things, I believe, with a manned mission to Mars is the fact that Mars does not have a magnetosphere. Are there anything in the works of restarting it, or how would you deal with something if you were to send a manned mission to Mars?
Again, I'm not totally an expert in that, but I think that they would have to just have their own shieldings. They would have to build their habitats so that they were shielded and safe in that area, yeah. The magnetosphere actually is, or the lack of magnetosphere is one of the key aspects in what may have caused the loss of the atmosphere. So because the Earth has an active magnetosphere, it sort of pushes out the solar wind particles and allows them to flow around the Earth, whereas on Mars, that doesn't necessarily happen. And so we think that maybe the atmosphere has been stripped off over the 4.5 billion years of the solar system.
Hi. So you mentioned that the level of salinity in the hydrated perchlorates is more severe than in the kind of salts we find here on Earth. Do we know of any extremophiles that can live in the conditions that might be present in that solution?
I know that my colleague Lori Barge is here, and she probably knows the answer to that question, but I, in fact, do not. Lori, if you want to stand up and give some people some insight, please feel free to get in line.
Thank you.
How is the Mars Reconnaissance Orbiter doing in terms of health and mission going forwards? And would it need to be replaced if there was some kind of major failure?
Yeah, thank you for bringing that up. I meant to mention that. Basically, I mean, I'm in love with our mission. I think it's the most awesome mission ever. It's actually, the spacecraft is very healthy. The instruments are pretty healthy. We have almost the same functionality as we had at launch. We have 20 years of fuel left. So, something could break because it is an aging spacecraft, but there's nothing that, seems like it's imminently going to break. So if we have fuel for 20 more years, we'll certainly be supporting, for example, the, landing site activities for the 2020 rover, and then, maybe we'll still be there to take those beautiful images of humans coming in to land on Mars. Who knows?
Hi, I heard Elon Musk propose to nuke the poles to release CO2 into the atmosphere. I just wanted to know if you thought that would be a viable option in the future.
So the idea is punching holes in the polar cap or something to get the CO2 out?
Yeah, to melt the dry ice that you talked about.
Yeah. I haven't heard that scenario, but what we know of the CO2 that's buried there, it's only twice the current atmosphere. So it's not enough to create a whole tropical environment or a whole, water sustainable environment.
So you're obviously collecting a tremendous amount of data. I saw hundreds of terabits. How much of that has been gone through, and how many sort of serendipitous discoveries are still to be found just because people haven't even looked at all the pictures yet?
A lot of the images do get looked at, but some of these things take the combination of a variety of data sets, and they take understanding this area and then understanding that area and then formulating a hypothesis and going off and targeting another area and studying that and slowly building up the whole picture. So, I mean, I can't quantify how much more we're going to learn, but I guarantee it's going to be a lot. Are there any other questions? Okay, well, I guess we're done then. Thank you so much for coming. I really appreciate it.